कैमरा तो स्टॉप ऑफ है, मुझे उसको तो करना जूम में एक बार आप दे दिखाएंगे तो एक बार हाँ
share it because they will share the screen. Huh?
I see. Okay.
Stop sharing for now.
Stop sharing.
Start sharing.
Okay. Right? Yeah, I saw from that.
Shubhavati has joined.
Yeah, I have joined. Hi.
Poonam, shall we start?
One moment.
So we have to admit, or Vandana has. Somebody else has to admit her, right?
Shikha, you can do.
Poonam, shall we start?
Can you hear me, Shikha?
Poonam, yeah.
Yeah,
Yes, we
can
can hear you.
you can hear, right? We can
Yes,
probably
yes.
start.
We are
I'll
very
just
clear.
take 2 minutes, 1 minute to just introduce our audience to the PAVINARI talks and just a continuation of our program. And then we can start with the GIPWG and IPA and so on. Hello, Shubhavati Di. So, welcome back to our second part of the celebration today. And this part is essentially by the Gender in Physics Working Group of the IPA, where we are hosting a talk which is called PAVINARI, Padarth Vigyan Ki Nariyan. The idea is to, celebrate women physicists who have made phenomenal contributions and somehow their names they did not get enough recognition during their lifetime. So this is the idea, and there have been already some talks that have been carried out at different locations by eminent experts in the area, typically senior women scientists. And we are absolutely honored and delighted to have with us Professor Sumathi Rao to deliver this next PAVINARI lecture. I would also like to just mention that, we have had very strong support from our Vice Chancellor, Professor Shantishri Dhulipuri Pandit, who has, supported who always supports the cause for, women in any field, and particularly in women in science. Unfortunately, she could not be here with us today. Additionally, I see that our dean, who was very much into, all the planning and the decision making and so on, and he lent strong support. He is here with us online. Professor Preetam Mukhopadhyay, he is unfortunately not here in town, but because we had the option of Zoom, so we have him here on Zoom. So I would also request him to say a few words, and then we can proceed with the plan of the program. So, Professor Preetam Mukhopadhyay, please.
Yeah. Am I audible?
Yes, yes.
Yes.
Okay.
Yes.
Yeah. Thank you, Poonam. I don't know where to start, but I start with wishing you all a very happy International Women's Day first. Is it audible?
There is a voice problem. Just one moment, please.
Yeah.
Call Saurabh. Saurabh. Yeah, now please speak. Yeah, please speak. Let's see if this mic works.
Yeah.
Yeah.
Yeah, Poonam, is it audible now?
No, no,
Am I
no.
audible?
Not really audible.
Actually, Zoom we can hear.
Yeah, we are able to hear.
Zoom we can hear
Zoom
him.
you can hear, but in the hall we cannot hear.
Yeah.
Uh,
Saurabh is not there, Poonam?
Saurabh ko bula ke le aao na. Who went?
Ask him to come.
Yeah, I'm just calling him. Please.
Yeah.
But Poonam, you can hear us?
We can hear you. I can hear you.
That's
We can hear
strange.
you clearly. This mic is also working properly. Oh, I see. So everybody is in the hall cannot hear you. Sorry, 1 second. Speaker is not working.
ऑक्स केबल नहीं होगा अपने पास डायरेक्ट ऑक्स केबल
Connected ही नहीं. Oh, yes. Yes, can you please try now?
Yeah. Audible now, Poonam?
Can you just try?
Please try now.
Yeah. Is it no? Saurabh, is it audible now?
Can you please try again?
Yeah. Is it fine now?
Huh? Please try now.
Yeah, yeah.
Please
Audible
try
now?
now. We cannot hear you.
Is it fine now, Poonam?
वॉल्यूम बिल्कुल नहीं आ रहा है.
यूट्यूब चलाओ यूट्यूब से क्लियर हो जाएगा.
यूट्यूब में देखना क्या आ रहा है. चेक इन द यूट्यूब.
यूट्यूब
कर दिया. Now
सेटिंग में जाना यहाँ पे तो हमारा
तुम बता.
साउंड सेटिंग का इसको माइक्रोफोन
नाउ होना चाहिए. ये पहले देखते हैं. Will committee room work better? All of us can sit there.
They can hear us, then let's proceed anyway.
Okay.
Can they hear us?
Let them
I mean,
stay.
can they hear
It will be
Sumathi
there.
Rao?
It will be recorded on YouTube anyway. So we can just do a local
Don't
recording.
get to ask questions, but yeah.
Let us make a.
it's an aux cable, right?
हाँ.
Same mechanism to be band
हाँ?
same mechanism.
करो करो एक करो. और इसमें बाकी कनेक्शन है. वॉल्यूम कम करो. Please try now.
Yeah, Poonam, is it better?
Yes, yes, we can hear you. Yeah, we can hear
Okay.
you. Please.
Yeah, yeah. There's an echo going on, Poonam. Mm.
Please go ahead.
Yeah, it's fine now. Yeah, I think so. Yeah, so first of all, I start with wishing you all a very happy International Women's Day. And I also thank Professor Mehta and Professor Prajapati for organizing this first regional networking meeting of women in cosmology, astroparticle physics, astronomy, and astrophysics, which is jointly organized by SPS and IUCA, Center for Astronomy Research and Development, ICARD. And this is a wonderful opportunity for the students and the other faculty joining and because it's also online streamed. So this is a fantastic opportunity to all of us to get together and uh, means have be part of this discussion and these talks. And I know Poonam has worked really hard to make this event successful. So I thank Poonam and Professor Prajapati for this event. I also thank the speakers, Professor Rao, Professor Sethi, Professor Jain, and Professor Rani to coming to SPS and being part of this event. And for part of this PAVINARI, the lecture series on women in series on women physicists, we are delighted to have Professor Sumathi Rao from ICTS Bangalore. So with that, I hope the event is already a very means is successful, and I'm sure everyone will be appreciating this event. And thank you, Poonam. Yeah.
Hello?
Yeah, Poonam.
Shikha, we can
Thank
hear
you.
Okay, okay. Can you hear me, Poonam?
Yes, we can hear you.
Okay, I'll just share my slides. Can you see my slides?
Yes.
Okay, Poonam, are you there? Okay, let me start. I think Poonam is there. Poonam, can you hear me? Kuntla, you can hear me, no?
Yes, I can hear
Okay,
you.
okay. So let me welcome, thank you, Dr. Preetam, for giving this introduction, and also thanks to Poonam for organizing this program. So we welcome
Thank you,
you all.
ma'am.
This
Yeah.
happens to be a celebration for International Women's Day, as well as we are also celebrating 10th Pavinari talk. To thanks to Poonam, JNU, and Sumathi for all this to take place. And this is a program under Gender in Physics Working Group of IPA, Indian Physics Association. So I'll just take 2 minutes and just giving a brief introduction of GIPWG and IPA.
ইউটিউবে তোমার অনলাইন স্ট্রিমিং হয়
So you can
আপলোড করা এটা ওটা অনলাইন তোমার
you can mute your mic, please.
লাইভ বড় ইভেন্ট
Maybe those who are not speaking, can you mute your microphone? There is some disturbance coming. Yeah, Shikha, continue.
So,
Yes.
so Gender in Physics Working Group.
Now it would probably work.
Yeah.
Shikha, if you have the control, you can see who is speaking and you can mute.
Actually, control is with Poonam.
Okay.
Kuntala, can you do this?
Yes.
Poonam,
just-
please mute others who are not speaking. Yeah. Yeah. So,
Yeah.
Gender in Physics Working Groups, just a brief introduction. So, IPA formalized GIPWG in May
Now it will work, right?
2017.
Now it should work.
This you should turn off.
With the mandate of coordinating national efforts towards gender parity in physics profession. And GIPWG focuses on addressing the challenges faced by women, fostering an environment of equal opportunity and recognition for all individuals in the discipline. And there are several gender groups like HEP, CMP, NAP, and Poonam Mehta is the chair of the HEP group, Deep Shikha for the CMP, and Sarmishta for NAP. And these focus on specific subject groups. So these groups organize conferences, workshop, panel discussions, as well as special sessions in physics conferences for raising awareness about gender-related issues for women scientists. So these are some of the activities which have been taken up under these GIPWG, for example, for Girls and Physics, for International Women Day, and on various occasions such programs are arranged. These were some also special programs which were earlier arranged. For example, Pressing in Progress in 2019, it was a big conference that was organized in Hyderabad, and IQIP conference in 2023, and there were other programs also organized, and Roni Godbole was part of this multiple choice question, and we always celebrate her physics as well as her contribution to women in science with our activities in PAVINARI and GIPWG. And the earlier PAVINARI series, these are the talks which have been held. This is the present talk is 10th. So it's very nice that Sumathi Rao is here with us for this talk, and she'll be talking on Emmy Noether. And we also have an ongoing survey, and I'll request, I'll be sending a link to all of you who are present here to kindly help us to reach as many women faculty in institutes and universities. And it's just so to get some information from them. It's a small survey. And with the special thanks to Poonam and her JNU team in organizing this, I will request Shubhavati to say a few words about the IPA. Thank you.
Thank you.
Shubhavati is the president of the IPA. Yeah, I'll stop.
Let me share. Can you see my slides?
Yes, yes, we are able to see it.
Okay. So is it in full screen?
Yes, it is in full screen, ma'am.
Okay, thank you. So thank you very much, Shikha. I am very happy that the PAVINARI is getting organized very frequently now under the able leadership of Shikha and the GIPWG team. PAVINARI was started in before the International Conference on Women in Physics in 2023. I and Vandana were the co-chairs, and we were in the GIPWG at that time, and we started this series. And first series there were about 6 talks, and then she has restarted. So it's really happy to see, and I'm also happy to see that it is happening in an university. So I am currently the president of IPA, as Shikha mentioned, and Gender in Physics Working Group is under the Indian Physics Association, and this was established in 1970 with the objective to help the advancement, dissemination, and application of the knowledge of physics. We have about total 5,000 members, 48 chapters all across India. IPA liaises with national bodies as well as it has the liaises with the international bodies like the American Physical Society, the Institute of Physics, then the Italian Physical Society, Australian Physical Society, etc. APPAs, and IPA has some memorandum of understanding. For instance, if the IPA member can get the APS, can attend APS conferences with the APS member rate, even if they are not APS members. IPA also has publishes the news bulletin quarterly, which is the physics news. It organizes special lecture series like D. C.V. Raman lecture series, PA Pandya lecture, IPA, IOP IPA, Homi Baba, Cockcroft Walton lecture series, etc. The C.V. Raman lecture and the PA Pandya lectures are happening now. Some of them has happened, and many of them are in the March, and then we also organize a young physicists meet. The latest was in Gandhinagar in February 2026. There are theme meetings and there are awards in various categories. And in fact, sorry, my slides are not moving.
You have to scroll down. Scroll down. Ma'am.
I know, but somehow it's not going. So anyway, then let me put it in this mode. And this is physics news. I already mentioned. I wanted to mention about the IPA awards because the IPA call is still on. The last date is extended. It's written here 28th February, but the last date is extended to 20th March. And we really request people present here to see if they can get nominated or they can nominate someone. There are many awards and the last date is extended till 20th March. I talked about the Young Physicist Meet, which was initiated in 2021. And to establish contact with the young physicists and the Gender in Physics Working Group, of course, Shikha talked about. So, and this is the IPA Executive Committee at present. And I would like to end with a call, appeal for joining Indian Physics Association. And, you know, we want new people, new ideas, and it will be really nice if more and more people become members of the Indian Physics Association. Thank you.
So, can you hear me?
Yeah, so now I will request Poonam to kindly introduce the. Thank you, Shubhavati. I'll request Poonam to please introduce Sumathi Rao.
Okay. So, it's my great pleasure to introduce. Huh? Echoing.
You can say you all directly. And on the mic, online.
This is fine. So it's my great pleasure to actually welcome and introduce Professor Sumathi Rao, whom I have known for my entire academic journey, so-called my research journey. Professor Rao is a distinguished Indian theoretical physicist. I would say a very broadband theoretical physicist because she started her journey in the field of particle physics, and then she when she came back to a faculty position at Institute of Physics, she made a strategic choice of moving from high energy to condensed matter physics, and in some sense, moving from particles to quasi-particles, and thrive in that new area. So no age is less to move on to new things, and there is no limit, no barriers. If you are interested and if you feel from inside, you can actually conquer the disciplines and try. So Professor Rao actually did her PhD from Stony Brook under the supervision of Robert Schrock in the area of, again, high energy physics. Then she moved to IOP, which I already mentioned, after which she moved to Harishchandra Research Institute, and there she has spent most of her career there working in the area of condensed matter physics, mesoscopic physics, Luttinger liquids, and so on and so forth. And currently the interests span wild semimatters, Majorana fermions, and topological materials, and so on. So the list is long, and I don't want to take away a lot of time from her talk, but I would also want to mention that, you know, Professor Rao has been instrumental in, you know, organizing schools, workshops, training younger people. So there was one very successful school on field theories in condensed matter physics, if I remember correctly, around the year 2000 in HRI, from which I think Professor Rajaraman was also one of the speakers in that meeting. And that was immensely successful because, you know, people working in the country at different places got together and they got the training from best of the minds. So I think she has a very important role in nurturing younger people. And in addition to that, I think a lot of credit to her because her PhD students have gone on to become prominent faculty members at reputed institutions in the country. I can name a few: P.K. Mohanty, Sorin Das, then Arijit Saha, and then recently Udit Khanna. So the list is impressive, and there are also people who benefited from her directly or indirectly, including myself. Yeah, this is something very interesting about her. You don't feel the age barrier with Sumathi. I remember, I'll just mention a small thing here. I remember when I visited HRI for the first time when I went, Sumathi said, please call me by name, you know, and it was not usual when you go from a university system that you call people by names. But that already, you know, breaks the barrier. So that was something which I learned, and I, of course, also encourage people to call me by name. So that's something which I have learned from her and other colleagues there. So that's something nice. I would also mention that, yes, she has got several awards and honors, including membership of Indian Academy of Sciences and the National Academy of Sciences, Third World Academy of Sciences, and recently as APS Fellow for her contribution to not only condensed matter physics, but also to the cause of, you know, strengthening gender parity in science, or encouraging younger female students to take up science as a career. I would say this is something which is an example of how scientific excellence and social advocacy are very much linked. So one can be good at both the disciplines, and that is because if you are scientifically weak, then your social cause suffers. If your social cause is strong and scientific content is weak, that also doesn't work. So you both have to go hand in hand. So that's very important, and I think Sumathi is a prime example of that. And with that, I would like to warmly welcome Sumathi to please
I'd like to first very warmly thank you for extraordinarily great introduction that you gave to me. But before that, I also wanted to thank IPA and the Gender and Physics Working Group for having started this series on PAVINARI, Padharth Vigyan Ki Nari Anke, this series of talks on these things. And in particular, I would like to thank Vandana Nanal, Shubhavati Goswami, and Shikha Verma for giving this introduction over here. So with that, let me start my talk. What I want to talk today about is about Emmy Noether's legacy. And I will, the title of my talk is Where Symmetries Become Law. And the plan of my talk is to first give a brief historical perspective of the theorem. And then I would like to tell a general audience what the theorem really means in as simple a language as I can do it. And then I also wanted to discuss a little bit about what its impact is on current day physics. And finally, I'll talk about her legacy as a woman in physics and what impact it has on women in physics today. So as many of you might know, the famous theorem that she has is that for every continuous symmetry, there exists a conservation law. This was stated in a paper in German called Invariant Variations Problem in 1918. And this actually led to a paradigm shift in physics. Now, for instance, all of us, when you look at a system or a Lagrangian, you first look at the symmetries of the system and then try to understand what are its conservation laws. Earlier, this idea of using symmetries of the system was not there. People knew about conservation laws, and that's what they tried to use. So it actually led to a paradigm shift in physics, which I'll discuss a little bit more about. Is it audible? Yeah. Yeah. So what was the problem that she was trying to solve? she was actually invited in 1915 for a, what happened? It's not audible here. Okay. Can you hear me now? Locally? Is this on? No, this is not on. It's on. Okay, I'll try to speak a little louder.
Yeah. A few rows you are very audible.
Okay, I'll try to speak a little louder. And because it's already gone on for long enough, we won't change the mic now. So what was the problem that she was trying to solve? She was actually invited by Hilbert and Clyde to Göttingen in 1915 for their help in understanding the conservation of energy in the general theory of relativity, because this was something we just started. This was the, what's up? Let it be as it is. So she was invited to Göttingen in 1915 for help in understanding the conservation of energy in the general theory of relativity, just after Einstein published his general theory of relativity paper. And she obtained the proof of an assertion by Hilbert concerning the connection between the failure of proper energy conservation laws and general relativity. I will try to explain what this means. But first, let me just say that these were the Noether's theorems, which was originally in German, and I've just given the way it was explained by Catherine Brading in September 2018, and where she's translated it into English. And the first one is what we call Noether's first theorem, and the second one is what we call Noether's second theorem. And I will write it more clearly in our words. Both the theorems are variational problems applied to something called an action, which is an integral of a function of some variables and their derivatives. Theorem 1 considers the case where the action is invariant under a continuous group of transformations which depend on constant parameters. This is what today we call global transformations. And theorem 2 considers the special case where the action is invariant under a continuous group of transformations, which themselves can depend upon arbitrary functions of the independent variables. And this is what we today, for those of you who may have done some amount of field theory, is called local transformation that leave the action invariant. And the actual concluding section of our paper in 1918 was that from the foregoing, we also obtained the proof of a Hilbertian assertion about the connection of the lack of proper energy theorems with general relativity. It's interesting to know that this particular theorem paper was presented to the Göttingen Academy of Sciences by Felix Klein, presumably because she was not a part of the academy. In fact, she may not even have been in the audience. And somebody else had to present her paper. But the point is that even though this was a conclusion, what she did was actually something which was far more general. She actually connected energy conservation with time translational invariance. And at a very simple level, you can think that energy conservation means that the total energy of a system should not change. You can, the energy, for instance, as the example I'm giving here is of an accelerating car, which seems to increase its energy, but that energy comes from burning fuel. So the energy of an isolated system does not increase. And time translational invariance essentially means that if you do an experiment today and you do an experiment tomorrow, the result will be the same. As you change time, it does not change the result. And at some level, these two concepts seem very different. So how are they related? And before explaining how they're related, for that which I'll have to tell you about Lagrangian mechanics, let me also tell you that Noether's theorem more generally says that every conservation law is a consequence of a symmetry. Time translation invariance, she showed, leads to energy conservation. Spatial translational invariance leads to momentum conservation. That also I'll give an example. And rotational invariance leads to angular momentum conservation. And there are other symmetries which you come across in particle physics and field theory, such as the global UN symmetry, for instance, which leads to charge conservation, and the non-abelian charges and so on. But let's see, how do we see this? And for this, I have to start with what is called the Lagrangian formalism, which is something that most of the master students here would have seen, or even at some level at the bachelor's levels. Let's just consider the Lagrangian for a single particle moving in one dimension. The Lagrangian, as you know, is kinetic energy minus potential energy. So L is half mx dot squared minus Vx. And what is called the action is the integral of the Lagrangian over time. And that's what I've written over here. S is equal to integral dTL, which is just the integral of the half mx dot squared minus Vx. The half is not seen very clearly. So essentially, the particle will follow the path of least action. Unfortunately, this is not coming. I don't know how to. Can one move this, or should I just show it this way? Is this visible to people online?
Yes, it is visible.
Oh, okay. Okay, then let me go back to the original way. Can you go back to the, so sorry, did I change something?
Okay.
Only change I can see is that the full that
Oh, stop
screen
share and
mode is
reset.
gone. Otherwise, everything is fine.
What is gone?
The full screen.
Full screen is gone, but can you still see it?
Yes, yes.
Okay, that's fine then. If it's visible, that's fine. Yeah, good. This was fine. Okay. So the particle will follow the path of least action. And now usually to derive the equations of motions from the Lagrangian, what you do is make a small variation in the path, infinitesimal change in x, because I've just taken the Lagrangian to be a free particle moving in one direction, not free particle, half mx dot squared minus Vx, moving in one direction. So we make an infinitesimal change in x and see how the action changes. So x of t goes to x of t plus epsilon t leads to the variation in the Lagrangian is given by mx dot epsilon dot minus dv dx times epsilon, which is the change in epsilon, which is the change in x. And this implies that the change in the Lagrangian is given by, this can be rewritten as the first term, which with the derivative on the epsilon going over to x, so that the entire thing is now multiplied by this variation in x, which is epsilon. So when we now integrate to get the change in action, the second term, being a total derivative, vanishes because we assume that the endpoints do not change under the variation, right? And this is how we normally, and then that is why we get the first term is equal to 0, which is the equations of motion of the system, right? It's just as you can see, m times acceleration is the force. For F is equal to ma is something that you get from, this is how you get F is equal to ma from the Lagrangian method. Now let's consider the same equation the other way around, because the derivation of this dl does not require the equation of motion to be satisfied. It's true even for an x of t, which does not satisfy the equation of motion. So now I'm going to turn the argument around and say that symmetries are of the action are transformations which leave the Lagrangian invariant. Or more correctly, the action, but let's just say for this purposes of this talk, the Lagrangian invariant. And for symmetries such that x of t satisfies the equation of motion, if I have a symmetry and I say now that dl has to be 0, and I tell you that it satisfies the equations of motion so that the first term is 0, then by necessity, the d dt of mx dot epsilon has to be 0. So mx dot epsilon is now a constant independent of time. It's a conserved quantity. So this is Noether's theorem, that if you have any symmetry, if you have a symmetry transformation and the equations of motions are satisfied, then you have to have a conserved quantity. So this is the simplified version of Noether's first theorem. If I now take just free particles with no potential, then L is just equal to half mx dot squared. From the Lagrangian, it's clear that there is no dependence on position at all, because it only depends on the velocity. Since it does not depend on x, if I make a change in position, the Lagrangian is invariant. And then in that sense, that notice the change in x goes to x plus eta naught. Now, I've already said that d dt of mx dot eta naught has to be 0. It is conserved or is up for arbitrary eta naught. If I can remove, since eta naught is arbitrary, it just means that mx dot is conserved. So in other words, momentum is conserved. So spatial translational invariance leads to momentum conservation. So this is a very specific example of Noether's theorem, right? And conversely, you can see that if there is a force acting on the particle, that is if v prime x is non-zero, then the Lagrangian would depend on x. Then spatial translation would no longer remain a symmetry. And then momentum will also no longer be conserved, because the force is dp by dt changes the momentum, right? So you can see that there's a one-to-one correspondence between the conservation of momentum and the spatial translation. So this is part of Noether's theorem. So this is the main point that I need to get across. So if this is there, then this is the simplest case in which you can understand Noether's theorem. And now one can do it for a field theory as well, where instead of just having a classical mechanics, you have a classical field theory. And the Lagrangian now depends on position, on a scalar field, derivatives of the scalar field, and so on. And you can again, even in this case, if those of you who would have done field theory would know that you can again get the equations of motions by the principle of least action by demanding that the change in action go to 0 under a variation. And this is what leads to the Euler-Lagrange equations of motion. And now let's see if the phi x is a solution to the equations of motions, and I take a transformation, phi x going to phi prime of x is phi x plus epsilon x times any function of, in fact, of phi of x and x, then the change in the action can, to first order in epsilon, it can always be written as epsilon x times some function, which I'll call k of x, because and one also knows that this has to be equal to 0 because it's the first order term which gives you the equation of motion. So we can see that this change of action is integral d4x epsilon x kx is always equal to 0. On the other hand, for an infinitesimal symmetry transformation, that is I take the epsilon to be now not a function of x, then we say for a symmetry transformation, the change in action has to be 0. And for constant epsilon, if I take out the integral d for x, any function has to be equal to 0. So we can always write this k of x as a total derivative, d mu j mu of x. And since we have already said that integral of this d mu j mu is equal to 0 for arbitrary epsilon, then whenever there is a symmetry transformation, d mu j mu itself has to be equal to 0, because this is true for arbitrary epsilon. This is again Noether's theorem in the Lagrangian case. I can integrate this expression to find the conserved charge. And again, I mean, you can integrate it over all of space, but you can integrate it the time derivative over all of space. You can integrate the spatial derivative of over all of space, and the combined sum has to be 0. But that automatically, the second term, if I take now the derivative, this always has to be, this term, the second term is always 0 because it's a surface term, right? So that gives you the fact that the derivative of j naught is 0. So q, which is integral of d cubed x times j naught, is the conserved charge. So this is the conserved charge in the quantum field theory, where j, the current, can be constructed from the fields in the theory. And again, for internal symmetries such as a U1 symmetry, the Lagrangian is invariant under the kind of a phase transformation. You take phi x going to e raised to I alpha phi x. Then these are things, if you have come across it, you will know that then the J mu, the conserved current, is written in terms of the fields, and then you can compute the charge. The point is that this is just generalization of what I said for classical mechanics, for a classical field theory. And till now, what I'm mainly talking, and the point that is important for a field theory is that when alpha is equal to, now you make this alpha to be a space-time dependent quantity, and it depends on x, then the symmetry becomes a local U1 gauge theory. And the second theorem of Noether addresses these cases and shows that in these cases, the conserved current has a slightly different meaning, because you also have to include the gauge fields in the system. So this leads to quantum electrodynamics. So in other words, what I want to say is local gauge symmetries lead to the interaction of forces. From the first theorem, we can get this nice connection between the conserved quantities and symmetries. From the second theorem, what we understand is that if you need the conserved currents, then you also have to include forces in the system. By itself, it will not be conserved because there will be additional terms which come because of the fact that the alpha is now a local term. It depends on space-time. And so that is what leads to these additional forces in the, gives rise to additional forces. For instance, an electric charge is always accompanied by a field, the gauge field, right? So you can't have, I mean, electric field and magnetic field. What I mean by gauge field here is just in normal language, electric field and magnetic fields. If you have a charge in the system, it has an electric field. If you move the charge, you have a magnetic field. Those come along with it. And so if you directly from the conservation laws of Noether's second theorem, you can understand that you have to include these forces or these gauge fields in the system. So that was the thing that these things are all just a consequence of Noether's theorem. And now, of course, you can generalize it to many more cases. So getting back to the problem of energy conservation, Noether's theorem, which is, when you think about it in purely flat space-time, it connects energy conservation with time translational invariance, which is the first thing that I said. However, if you go to general relativity, the components of the metric are themselves gravitational field variables. And in general, they are themselves space-time dependent, right? So this is a case where it's a local symmetry. So it's something which will be when Noether's second theorem has to apply. And since the energy conservation momentum tensor contains contribution only from the matter fields and not from gravitational fields, you cannot try to conserve it in the same way that you did it earlier in special theory of relativity, which is what at that time in 1915 people were confused about. Instead, by her theorem 2, the variational principle led to what are called now the Bianchi identities for general theory of relativity. So it kind of constrained the gravitational field. So this was all coming together at the same time when Einstein wrote down his GTM. So this was what clarified the meaning of energy conservation in 1918. So now I'll come to the next part of my talk, which is the impact of her work on current day physics, right? The impact on particle physics is profound because, as I said, the relationship between conservations and laws and symmetries were what led, I mean, people didn't know what the forces between the elementary particles were. So it was these relations which led them to understand that the elementary forces between the particles are given by this SU3 color cross SU2 left cross U1, basically led to the standard model of physics. And even today, it guides modern theories because physicists, whenever you now want to look for any, when you write down a Lagrangian, you first look at its symmetries, write down the conservation laws. You look at a system, look at what symmetries it satisfies, write down an appropriate model for it, and then study it, right? So even today, this has led to particle physics prediction of new particles via symmetries such as SU5 symmetry, grand unified theories, supersymmetry, and so on. And then the Higgs mechanism, which was a way of giving masses to particles without breaking underlying gauge symmetries. Because now we understand that if there is a ground state of the system, then e raised to I theta q, where q is a conserved quantity, conserved Noether charge, is also a ground state since the Hamiltonian commutes with q. And these ground states are connected by these Goldstone bonds. And so these are not only in particle physics, they're directly relevant as phonons in lattice systems. And in the standard model, of course, they're relevant in giving masses to various particles. And there's a lot of impact on condensed matter physics as well. I'll give a particular example here. Because there are a lot of quantum phases where you don't understand exactly what the symmetries are. And many times people do numerics to understand phases of quantum matter. And an interesting example, which may not be completely familiar to all of you, is the Neal to valence bond transition in a spin model. What is called the Neal phase, which is the up-down, if you have a antiferromagnet, the spins arrange themselves in an up-down configuration. That's called the Neal phase. And that has order parameters of Sx, Sy, Sz, where the continuous symmetry is SO3. And the conserved quantity in this case is the total spin. Then you have something else called a valence bond solid, which has order parameters Vx and Vy with a U1 rotation symmetry between them. And the conserved quantity here is related to Skyrmion number of the Neal field. This may not be very familiar. I'm just trying to say that at a critical point, what happens is that from numerical simulations, people found that instead of an SO3 symmetry, there was an emergent SO5 symmetry, which connected all these phases. And then when you apply Noether's theorem to this new symmetry, then you find new conserved charges. And people could go and look in an experiment for these new conserved charges and find them. So in that sense, it is completely relevant even here. And in general, in condensed matter physics as well, you first identify the symmetries and then write down effective field theories. Because even in condensed matter physics, even though you know the lattice and the underlying, the basic interaction, which is the Coulomb interaction, you often cannot write down everything from microscopics. You have to often use symmetries of the effective theory and then write down the theory. So the essential point I want to emphasize here is that Noether's theorem remains a cornerstone of modern theoretical physics, because what is most important is she provided the link between symmetries and conservation laws. So with this, the technical part of my talk is more or less over. I would like to say a little bit more about her personal life as well, and also how the legacy of this. She was born in March 23rd, 1882, in a Jewish family in Bavaria, in the town of Erlangen, and her father was a professor of mathematics. But she initially studied as a language teacher, because that's what women did in those days. And later on, she switched to mathematics, and she got a PhD in 1907. And she was the second woman from that place to get a PhD in physics. But she was not appointed as a faculty or anything. She had to teach. She taught in Erlangen for several years because her father was not well. She would take lectures in her father's name. And these are some pictures of her in the early years. And this is with her family, her brothers. And then the last one is in a later time. And then, as I said already, in 1915, she was invited by Hilbert and Klein to join the maths department in Göttingen. But she was actually prevented by, I mean, they had a vote and the other faculty members prevented her, even from other departments. And there's a very famous anecdote, I don't know true or not, where Hilbert is supposed to have declared at the faculty meeting that I do not see the sex of the candidate as an argument against admission as a professor. After all, we are a university, not a bathhouse. But male faculty still argued that men would not want to learn at the feet of a woman. That time, this was around 1914 to 18 and all, when First World War was going on, and there would be soldiers and all that. What would they think of they had to learn at the feet of a woman? So she actually spent 4 years lecturing under Hilbert's name before she got what is called, in Germany, you have to get this thing called habilitation before you can be an independent professor. Even after that, she had to lecture as an unpaid extraordinary professor. And it took another 4 years before she finally started getting paid. And she supervised more than a dozen doctoral students.
This was at Göttingen. She became faculty
In Göttingen.
In spite of the opposition.
In spite of the opposition. Many years later, but she did become a faculty. So unfortunately, soon after that, the Second World War problems started. But yes, she became a faculty. She had doctoral students in early years with her father and later with Edmund Landau, since she was not allowed to supervise dissertations on her own. But finally, as I said, she did receive some measure of recognition from her colleagues. And it looks like her colleagues were not the ones who were against her. It was the rest of the departments, other departments as well. She received, along with Emil Artin, the Ackermann Tubner Memorial Award for contribution to mathematics in 1932. But unfortunately, she was fired from the university in 1933 by the Nazis. This time not for being a woman, but for being Jewish. So along with many other Jewish faculty like Max Born and Richard Curran. And this is the time many of the Jewish scientists from Germany and other parts of Europe left and went to US. And there was something called an emergency committee in aid of displaced German scholars. And because of that, she was offered a position by the Bryn Mawr College in the US. This is a women's college. And she was only offered there, whereas most of the other men went to more famous universities. And there she actually guided several women postdoctoral, but it was good because she guided several women postdoctoral fellows who went on to do mathematics. And she had one doctoral student called Ruth Stoffer. She also lectured at Princeton universities without honorarium. This is also something which I was really surprised. Unlike other 17 other male visiting lecturers whose names we probably don't even know now, right? But she was never paid for her visits to Princeton. But she died within a couple of years of moving to US in 1935 at the age of 53 by some medical complications. Noether was the first woman invited to give a plenary lecture at the 1932 International Congress of Mathematicians in Zurich that year. And the next time that happened after 1932 was in 1990 in Kyoto, when Karen Uhlenbeck was invited. And she later went on to win the Nobel Prize. So in the intervening years, nobody was, and I don't know even now after that whether anybody has been. And I thought before I go on to her legacy, I'll mention one more thing, because I also wanted to mention the earliest women theoretical physicists from India. I mean, of course, we did not have anyone that early, but still, there were some women in the 1960s who did their PhDs in India. Professor Alladi Ramakrishnan, after returning from the Institute for Advanced Studies in 1958, began a theoretical physics seminar in his home, family home. And there were 4 women students who attended this: Bhamati, Tanga, T.K. Radha, and S. Indumati. And calling them the Indian Quartet. It seems that Nehru was so impressed by the fact that there were 4 women attending this thing. So that actually helped in setting up math science. There was somebody who came and said that, I mean, they then went to ask him for permission to have this math science over there. And because of this, he was so impressed. And also the fact that there were 4 women in the audience. This is something that I recently came to know, but T.K. Radha was a PhD in 1962, was a postdoctoral fellow in Stanford under Leonard Schiff, whom many of you would know from his quantum mechanics books, right? And she had papers with Schiff and Marshall and 14 papers in particle physics at that time. She joined the Institute of Advanced Studies as a visiting fellow for a year with Oppenheimer, and then she moved to Edmonton post a marriage to somebody called Vembu Gauri Shankar, and then they never found her name also again, because she dropped out because of children. And then 1 decade after dropping out, she took computing courses at the university, worked as a programmer and helping physicists with the numerical computations, and sometimes contributing her own ideas. And some papers have a name, except it's now Radha Gauri Shankar. So people did not initially connect them. Many people here they're not too many older people, may know Bhamati, who was a PhD from Madras University, postdoc at the University of Colorado, and she rose to be the head of the department of Madras University. And she later married E.C.G. Sudarshan in 1992 and moved to the US. These names were discovered after a 2018 blog post, Grandma Got STEM, by Richard Levy. And I just thought, found the pictures as well. And I thought 3 people, Radha, Vamati, and somebody else called Amba Raghavan, who, I mean, now when I see it, she was a very famous, very good physics teacher in one of this Jabalpur or somewhere like that. And then she's moved to the US, and the 3 of them getting together in 2018, from 58 to 2018. And this is somebody many of you might know. This is Professor Bimla Bhuti, who recently passed away. And she worked under S. Chandrasekhar in plasma physics. She worked at IIT Delhi and later at PRL, and later moved to IPR to form a new institute. And she has many firsts in India to her credit. First Indian woman physicist, fellow of the INSA, APS, Academy of Sciences of the World Academy of Sciences, what it's called, Vainu Bappa Award, Vikram Sarabhai Award, Meghnad Saha Memorial Award, R.D. Birla Award. She was also director of plasma physics at the ICTP in 1985 to 2003. And I gather from Poonam that somebody is going to be speaking about her. From IIT Delhi will be talking about her soon. So this is just her pictures. So with that, let me come back to the legacy of Emmy Noether. While most of us know Emmy Noether because of Noether's theorem, She is considered also as one of the most important mathematicians in the 20th century and worked in the fields of abstract algebra, which she revolutionized. Since I don't know much about it, I'm just saying what she said about her work what she said in her own words, that any relationship between numbers, functions, and operations become transparent, generally applicable, and fully productive only after they have been isolated from their particular objects and been formulated as universally valid concepts. So this is what she did in the Noether's theorem, and I presume that the same kind of thing is what she used in a mathematical work as well. Her students, called Noether boys, carried her maxim into the next generation. And I'll also mention the various tributes she got from various people when she passed away. Before Noether's theorem, the principle of energy, conservation of energy, was shrouded in mystery. This is what was said by Fraser Gurney. On her work on invariant forms, I'm impressed that one can comprehend these matters from so general a point of view. This was by Einstein. And in her obituary, Einstein said, in the judgment of the most competent living mathematicians, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. And she's widely known as the mother of modern algebra. I'll also mention that I'm calling these somewhat backhanded compliments because it mentions her sex. Greatest mathematician, greatest, I firmly believe that her sex has ever produced. That's a kind of not so kind nice and a great woman. Miss Noether is the greatest woman mathematician who has ever lived, and the greatest woman scientist of any sort now living, and a scholar at least on the plane of Madame Curie. So even as somebody, she's always mentioned as a woman. But even though she did actually get recognition later on in her life, I want to say that we should not romanticize the belated and posthumous recognition she got. We don't know how many more Emmy Noethers we may have lost because there has been so much of prejudice and they may not even have come up. So new insights of the kind that she had maybe have never emerged because she was born, they were born a woman and did not get the kind of backing that they should have. It's considered unsuitable for intellectual pursuit. This is also, a quotation from somewhere, I forget now. So it's absolutely imperative to have diversity and equity. In India, I would say not just for gender, but for all underrepresented groups, because you don't know where brilliant ideas might come from, right? Women, in India, there's a lot more of, or even all over the world, there are a lot of people who are just cannot come up to the level where their brilliance can be recognized. So we have to make sure that this does not happen. So to conclude, every conservation law that we understand today is a legacy of Emmy Noether. And physics was actually transformed because her voice was not silenced, right? That's why we know about it today. So if we want future Emmy Noethers not fight to be heard, then diversity must shape the future of science. Symmetry shape the law of nature, diversity should shape the future of science. That's what I think. So with that, I'll conclude.
Thank you, Sumathi, for this brilliant overview of the journey of Noether, also the Noether's theorem. Questions from the audience?
Sumathi, just a general question about her life. Did she ever have a spouse or children or whatever?
No, she did not have. She was not married.
Take a comment that there is a gift from the lecture every year. It's a big honor.
Yeah.
And recently, Nina Gupta from Einstein, Kolkata,
Yeah, I don't know if I'll just mention it again because I don't know if the online audience can hear it.
Yes, we couldn't hear it. Yeah, that's so kindly.
So Riddhi is saying that, okay, the first question was whether she was married and had children, where the answer is no. And the second question, Riddhi is, it's not a question, Riddhi is making a comment that every year that the Emmy Noether lectures are held. And this year, Nina Gupta from ISI Kolkata gave the lecture. The only Indian who has given this lecture. It's given by a woman mathematician. So,
the human materials, topological materials and all this, for instance, Z2 invariants, they have anything because it can be derived from Rogers theorem. I mean,
if Z2 invariance is a discrete symmetry, so Noether's theorem is more about continuous symmetries. So I don't think directly discrete symmetries have anything to do with Noether's theorem. But any
Sumathi, we are not able to hear you. Sumathi? Poonam? Poonam?
For some reason that is muted. That is the problem. Suddenly it got muted.
Yeah. Let me tell Poonam.
Hello.
Yeah,
Hello.
good, thank you. Now we are able to hear you. It had become mute. Yeah.
Did I get muted? Okay.
Yes. Yeah, your last, for few minutes you were muted. Yeah.
I see. Sorry. No, there were just some questions from here which I was answering. So maybe I moved a little further away. That's all.
Are there questions from the?
Had become muted actually. Yeah,
comments?
your mic.
You can unmute yourself.
Now it is fine.
Yeah. Ajit probably wants to speak, right?
Yeah, I had a question, Sumathi.
Yes.
Hello, Ajit here. Yeah, very nice talk, Sumathi. Thank you.
Thank you.
You had mentioned something was fermion number of the Niels field.
I'd mentioned what?
Fermion number of the Niels field.
Fermion number. Yeah.
That got me confused because fermion number looks like a topological charge. And
Yeah.
I would think topological charge had nothing to do with Noether's theorem.
Yeah. Per se, that is true. The topological charge has nothing to do with, I mean, in the sense, but this here, the fermion number that you're getting is probably from an effective field theory. So it is a continuous symmetry in that sense. And at that critical point where it becomes SO5, it becomes a continuous symmetry.
Okay.
So it's a topological charge, but it's still a charge which is coming from a continuous symmetry. It's not
So
like the Z2 charge, which I said was a topological.
No, I understand. But the conserved charge is the binding number or not? It's fermion binding number. No, I suppose conserved charge must be its fermion binding number.
Is that a fermion binding number?
Must be.
Must be this fermion binding number, but I think at that
yeah.
point it probably becomes a continuous charge, and hence it can.
Right. But binding numbers, I thought have don't relate to Noether's theorem.
Usually do not come from Noether's theorem. That's right.
Okay. Thank you. Okay.
Yeah.
We started from Lagrangian.
Yeah.
So there are ways to find the symmetries in a Lagrangian.
Yeah.
But before we can go to find the symmetries in the Lagrangian, we have to write the Lagrangian
theory in the Lagrangian.
So, but the T minus B, that's a very, it's an artificial.
No.
artificial kind of Lagrangian instead of P minus P for very simple systems. Right? How do you formulate the correct Lagrangians? How do you formulate correct Lagrangians in your theory?
The fact that the Lagrangian is kinetic energy minus potential energy is a general statement, right? So that is always true. I mean, yeah, I don't think you have to change. No, I didn't understand what exactly you were trying to say.
Formulate the correct Lagrangian for a given system.
For a given system, I mean, you in classical mechanics, you know, you will put whatever the constraints. So in other theories where you don't know the things, it is not easy to write down what is the Lagrangian. You have to use experimental evidence, and you have to guess what is the theory, and you have to look for. I mean, you have to think about what are the symmetries. Like, I mean, that even before you write down a theory. If, for instance, there's a charge and it's radiating in all directions, you will know that it's rotationally invariant, right? So that's how you will formulate your theory.
Observation, back guess the
Yeah.
give the correct.
Yeah, and sometimes you may not understand everything about the theory just from the experiments. Then you write down a theory, you analyze it, then you go to different limits of the theory, then you analyze it. And at different limits, different things may appear, right? So, yeah, Noether's theorem is more a mathematical thing, right? So it's telling you the equivalence between things, but it isn't telling you how to write down the theory for a okay, it is telling you how to write down the theory only in the sense that for certain symmetries, when you already know those that like this, I was saying for the local gauge invariance and so on, you know that if that symmetry is there, then the conservation law is there, then the conservation law sometimes can lead you to forces. Like for QED or for QCD, right? Because you know that you have to write down in terms of a covariant derivative. So it tells you what kind of gauge fields can come. So, Devashish, can you, I don't know what exactly he's asking. So, okay, you're not right. Okay. Yeah. Okay. I don't know what level he's asking, so I was asking. What? Last year. Okay. Yeah. Are there any other questions? Okay, then no questions here, I guess. So online, Shikha and people, are you still there?
Yeah,
Sumathi,
Sumathi,
it was really very nice. Really very, very nice.
yeah, Sumathi, very nice talk.
Okay, thank you.
Yeah, thank you very much. And with this, I think I don't see any questions on YouTube. So big thanks to you, and then also to Poonam and all the members who are present online. And then I have a special thanks to also Shubhavati, Vandana, Kuntala, Moon and Sudipta, who has especially helped in this series of PAVINARI for this particular series. All the GIPWG members, all the IPA members, and then of course again a special thanks to the GNU team, all the participants who are present in the center and also online. And Poonam Mehta, thank you very much for taking care of all these activities. Yeah, thank you very much. And she had a special program today morning also. So thanks for that. Okay. And Sumathi, thank you very much. And we are celebrating.
Thank you, Shikha. Are there any questions on YouTube?
I did not see any.
Okay,
Poonam.
fine.
Yeah.
Okay, fine. So we can come close to conclusion. Are there any other questions from the audience? No? Then one of our young students wants to narrate something or some incident or some story. Go ahead.
So what I want to tell you that an experience of mine. So when I joined in my bachelor's, I studied in a women's college, Providence Women's College in Calicut in Kerala. So there, during the orientation program, one of the teachers, her name is Dr. Bindu Amat, she mentioned something like she plotted a story. She actually gave us a story in which she told us some characters. Like she gave characters of there is a room. In that room, there is an advocate, there is a collector, and a police officer, and and a minister. And she asked, she gave us a task to give your favorite person, actor, actress, or whatever you want to give a face to the characters. So most of us gave male figures to those characters. And then when she asked the who is collector, which name you given to the police officer, the advocate, most of the superior classes of people, it was from a male figure. And then she asked, if this is what you are imagining, then how can you change the world? And years later, here I'm in GNU and I'm attending Sanjay Puri sir's class. What I want to tell you, when he gave us examples, like he drew diagram of phase transition, and he gives examples like, yeah, there is an experimentalist, and he uses she. I was so happy to hear that when you say she, and thank you so much for that. Thank you, everyone. Yeah, this is what I wanted to say.
Very nice. So maybe we can conclude. We'll just close the session then. Thank you, Shikha, Shubhabati.
Yeah.
Deep,
Thank you,
and,
Poonam.
everyone else who is present there.
Yeah.
So we'll
Thank
close
you.
the session now. Thank
Sure.
you.
Thank you.